Hi, my name is Jeroen Lenslots and I'm from Siemens PLM Software. Welcome on this web seminar on the fundamentals of sound source localization part 2, the advanced methods. In the first part of this web seminar, we saw that the main applications of sound source localization are acoustic troubleshooting and the assessment of different variants. We saw how you can use sound source localization to visualize to stakeholders where sound is actually coming from. We also saw that beamforming and near-field focalization are the main techniques, and that we determined that the quality indicators of sound source localization solutions are spatial resolution, dynamic range, and the ability to measure in the near field. Now in this part, we will focus more on what methods there actually exist to improve localization in low frequency. We will have a look at what is quantification with sound source localization, and we will also have a look at what Farfield deconvolution is. The first one I want to discuss with you is a technique which is based on near-field acoustic holography. Near-field acoustic holography is a technique which uses a regular microphone array. So it uses microphones which are all spaced at the same distance, and it has some the nice thing about near-field acoustic holography is that it can give a very good spatial resolution, maybe the best in class, but there are some side effects to it. First of all, you need to be in the near field. It's called near field acoustic holography, and with near field we really mean near field 5 or 10 centimeters from the source. Secondly, we need to cover the complete object. So if we have an engine of 1 meter, we really have to have an array which is 1 meter wide. Next to that, its lowest frequency is determined again by its array size, but also its highest frequency is determined by the spacing between two microphones. So if we have a big object and we are interested in high frequencies, we need to have a big array with a lot of microphones. So that adds up to a very complex measurement task. It could be that to cover an engine of 1 by 1 meter and being interested into frequencies up to 5-6 kilohertz, you might need 400 microphones. That is a high cost. You could decide to split that in batches to measure with a line of microphones, but then still you would need 20 measurements of 20 microphones. So it's really a big project to do that. You cannot have a holography results in 2 minutes. But the reward is big because it gives you a very good spatial resolution. Now, the holography method can actually be reformulated such that it fits microphones with an irregular microphone spacing. And now it happens to be so that for beamforming, we like to have these spherical or round circular microphone arrays where the microphones are not spaced regularly. And by using this method, and we call that in irregular near-field acoustic holography, to use that formulation, we can actually apply it on the same measurements we already did with beamforming in the near field. And that results to a third method that we can actually use together with the beamforming and the focalization that I already discussed. Now on this slide, you see actually on the left typical results from beamforming, and then we're focusing mainly on spatial resolution. Of course, in high frequency, 6 kilohertz, we see really nice red spots on those two loudspeakers. In mid-frequency, and here mid-frequency we used the 2 kilohertz 1/3 octave band. So the left picture, you see actually a relatively good separation of the two loudspeakers, measured at 60 centimeters. So even though they're not completely separated, the hologram that we see over here is quite convincing that it's in fact two sources. However, if we look at the same measurement in low frequency, and here we used the 500 Hz 1/3 octave band, measured at 60 centimeters, we actually see one big red spot. We see the picture of the two loudspeakers behind it, so we really know that spatial resolution is not good to separate those two sources. Then we take our array and we move it into the near field. In this case, we position it at 15 centimeters away from the source. at 2 kHz, 1/3 octave band, the picture in the center, we actually see the two loudspeakers, we see the two sources, they're very well separated. At 500 Hz, we see a kind of ellipsoid type of shape of hologram. It's because we know the real true sources, we can justify that this is the beginning of the separation of two sound sources, but it does not give a very convincing proof that we're really talking about two sound sources over here. However, we can then use this iNAH method, this irregular near-field acousticography method I was just discussing, and we can actually apply that method on the same data we already measured at 15 centimeters, and then we get a very nice source separation like you see on the top right picture. So even though with the spatial resolution calculation I just said and the expectation that the spatial resolution is proportional to the wavelength, where we could already predict at 500 Hz that's not going to give a good result, we can actually improve that result with a simple recalculation and get a very nice source separation of these at this low frequency. So just for the record, these speakers were positioned at 27 centimeters distance. Now we actually have three methods. How can we use them in a real case? Now, the best thing to do is to start in the Farfield. And we know in the Farfield we will have our beamforming solution, our beamforming method. And it will give us on our big test object, we can see, well, first of all, we can see the full test object. And second, it will give a good overview of the different sound sources that are available, that are present in this big object. And we might see a big red spot somewhere that we are interested in. In the second step, we then actually move this array into the near field at 30, 20, 15 centimeters. Yeah? And we're going to zoom in on this big source that we identified in the far field. Yeah? And as you can see with the green dots, we might find that this big red spot is actually consisting of multiple sound sources that we could only identify and separate by moving closer. And if we then still have a lack of spatial resolution in low frequency, we can actually apply this iNAH technique on the same measurement to really boost the spatial resolution in low frequency. So this is a typical application case we apply many times. So to give you an idea on a real object, here I have an example of, we did on the top left a measurement at in the near field, and we're analyzing the 800 Hz 1/3 octave band, and we don't get a very good result. It gives us some indication. Yeah? The same data set can be reprocessed with iNAH, and we actually see that it appears like it consists of multiple sources. I also had a look in a little bit higher frequency, in this case the 3150 Hz octave band, and there you can actually see that we find three sources. So actually there is a correlation between what we find in low frequency with iNAH. We have the suggestion that there is a sound source on the, if you consider the top right picture, in the bottom right, there appears to be a green sound source, which you don't see in the vocalization result, but it is available in the iNAH result. If we compare that with something which is much higher in frequency, we get some confidence that this is a good result. Because in the end, if you have a real object, you never know which are the real sources. We have a technique which can identify these sources, but there's always discussion on what the physical meaning is of those sources and how representative they are for the real situation. I mentioned in the introduction that we can also quantify sources. And with quantifying, I mean that we can estimate the sound power of a different component or a different zone. The way it works is like this. If we apply this iNAH technique, we actually get results in sound intensity, as you can see in the bottom at the unit of the color axis. So watt per square meter. So if we then draw a rectangle around that hologram, and we multiply the sound intensity with the physical area that is represented by that rectangle, we actually get sound power. So we get, in this case, the sound power of either the entire engine, or we can actually identify different components and we can compare them. So that's something, as we can see in this next slide. We can see that with, in this case, an academical example, but you see 3 different volume velocity sources, 3 different sources, and we can actually calculate the sound power of each of these 3 sources. Now you might say, how does that compare to techniques as the normal ISO sound power techniques? We can actually prove that if we are close enough to these sources, that we can be within 1.5 dB of the true sound power that you measure with ISO sound power techniques, which is within one of the engineering precision grade criteria that are defined in such ISO standards. So it can give you a very good estimate of the sound power. Another interesting technique is what we call source separation using a reference sensor. And we do that by calculating the coherence or the anti-coherence of the sound with the microphone array. So we use a reference channel, which is usually a microphone or an accelerometer, which we measure at some of the suspected source locations. In this slide, on the top, you see a car, 2 sources on the outside, and with a big array, we can actually look on the outside and we can calculate where the sound is coming from. And you will see that there at the wheel, there's a bigger source, and there at the windshield, there's a smaller source. But for this type of object, a car, it's actually more interesting to look at what is audible on the inside. In the end, somebody's driving that car, and it's that person that will be affected by that noise. So what we then do is we place some extra microphone, in this case, inside the car at the driver's ear, and then we recalculate the sound which is coherent to the reference microphone. And then suddenly you see the bottom picture, and it proves that the source which was at the side windshield, the side door, is much more important to the driver than the source at the wheel. And in this case, for this car, the firewall of the car has of course been designed well enough such that that sound at the wheel is not propagated to the inside of the car. So it's a very powerful technique to see what the influence is of sound sources to operators or users of your products. Then I come to the technique of Farfield deconvolution. Farfield deconvolution is a technique which also improves the spatial resolution in low frequency, but now when we measure in the far field. Sometimes it's just not possible to really measure in a near field, even though we know that gives the best results, but it might be physically impossible to measure so close. Like if you have an engine on a test bench, there's all kind of tubes sticking out and components sticking out, so it's sometimes not possible to measure very close. And techniques like Farfield deconvolution can then help. It's a kind of iterative methods. It's also quantitative, so it gives sound intensity results that can be used to estimate the sound power again. And it typically increases the spatial resolution up to a factor 4 or 5, depending on the case. And as you can see on this picture, in the bottom left, you see how you can improve from a beamforming result into where you have, well, we know there are two sources, but you cannot really see that it's two sources from the hologram. And on the right, we see the Farfield deconvolution result that can really separate those two sources. The deconvolution works more or less as follows. First, we measure the sound with a microphone array and we calculate a beamforming result, just as we did before. Taking a look at these beamforming results, we assume that at all the hotspots in this beamforming picture, there are monopole sources. Those monopole sources generate a sound field. We can use functions like green functions to estimate what kind of sound field these sources would generate if they were real sources. Yeah? So we calculate mathematically or analytically what kind of measurements, what kind of pressures these monopoles would generate on our microphone array. So that's what you see. I followed now the pictures. I'm now at the bottom right picture where we forward propagate the sound to, where we forward propagate these monopoles to our measurement array. Yeah? And then we compare what we analytically calculate that they should make with what we really measure. And of course it's different. There's a difference between the two. And based on that difference, we will change the position of those monopoles a little bit, such that they better match the sound field that we really measured. So we do that in a couple of iterations until we are satisfied with the result, or the difference is small enough, or we satisfy some kind of a stop criterion. There are different classes of deconvolution. Some are based on some kind of least squares method to actually determine the step into the to change the monopoles more into the direction where the sound is, such that matches the measured pressure field. Others are also based on a kind of cleaning, an iterative cleaning, where they say each time we take one monopole and we use a method to actually remove that monopole completely from the measured data set, and then we take the next one and the next one. So there's a couple of different methods. They go by the names of Damas, Damas2, Sira, but also Clean, Clean SC. Yeah? How can this help you in a real case? We know these methods are very well when they are used on uncorrelated sources, for example, in a wind tunnel. On this slide, on the left, you see a typical beamforming result in the wind tunnel. We had to hide the car a bit to protect the source. That's why it looks so strange. But you still see the hologram, and you actually see that there's a source at the wheel. There's also a lot of other purple energy at lower level sources at some place. Just to give you an idea, the wind is blowing 140 kilometers per hour, and the distance of the array to the source is almost 4.5 meters. Yeah. On the right, we can see the improvement we can get with Farfield deconvolution. So you see the source at the wheel is much more precise at this case. We also see that there is actually, or on the left, we see more like a blurry picture around the windshield and the side mirror. But on the right, we can actually see that the side mirror is much more pronounced, much more identified. Yeah. So we can actually more accurately locate sound sources there with a better spatial resolution and also a better dynamic range. On the right, yeah, they're both 10 dB dynamic range. On the right, you can actually also see that we draw a rectangle around the wheel, and we can actually quantify that, so we can estimate the sound power of that component, and we can rank them in plots like you see here on the inset. Now that's a lot of theory. Let's have a look at a couple of real examples. There's also more complex cases, and one of them which I like is like what I call the OEM versus the supplier challenge. So you have a manufacturer which has suppliers, and he maybe has design targets for these suppliers, and the supplier delivers a component which has to be integrated into the big machine of the manufacturer. It can be, for example, a pump or a turbocharger that has to be integrated into an engine. Now the supplier usually has to prove that his component does not exceed a certain sound power radiation. Yeah? At the other hand, the supplier also knows that his component will be integrated into the machine, the engine of his customer. Yeah? And then if you measure on the outside with sound source localization techniques or with other techniques, it might be that the total sound power of this machine is too high. So what do you do then? How do you prove as a supplier that it's not your component, but that it's the way it was integrated? And that's a typical task for sound source localization, where we use these sound power techniques to identify an area. As you can see here on the right, actually we define a zone on a 3D model of the engine, so not a 2D plane, but a 3D model. And they're doing an analysis of the behavior of that component in different octave bands and also in different operational conditions. So we're maybe used to looking at operational changes in operational conditions in the terms of color maps and waterfalls, where we track, make plots of frequency versus rotational speed, and then we look at sound pressures and we can identify orders. But here, 1, 2, 3, 4 critical operational conditions, so 1000 RPM, 1500, 2000 and 2500 RPM are all assessed in a almost stationary way, and we're actually assessing in which octave band this has the what the sound power is of that component in those different octave bands. And that helps suppliers and OEMs together to improve the components and also the way it was integrated into their products. So in this case, that is interesting. The sound source localization result, the hologram, it's not the end result, but in this case it's this picture which you see over here, which is just a bar chart. I think it's even made in Excel. That actually is the end result of a measurement campaign using a sound source localization tool. And based on these type of plots, the supplier and the OEM can decide on which part of their products they need to further work on to get the highest reduction in sound power in this case. There's another example here on the same theme where it shows more the OEM point of view, where in this case we have a turbocharger. And with a turbocharger we often have a complex way to attach this turbocharger to the rest of the engine. So there's actually tubes, yeah? And many times it's not the turbocharger, but it's the way it was mounted and connected to the rest of the engine. And making these 3D plots like you see on the bottom right allows actually to show that here it's indeed at the tube where there's very high noise coming from, that it's not the turbocharger itself, but it's the way it was integrated. And these studies really improve the knowledge of how this noise is radiated, and they can also prove how the supplier of the components can be compliant to the specification that he got to with respect to sound power. So here we come at the end of this web seminar on sound source localization. We already learned the main applications of sound source localization. We already learned about beamforming and near-field focalization as the main techniques, and we already learned about the quality indicators of sound source localization solutions. In this advanced part, we learned how we can actually improve spatial resolution and low frequency with two main methods. One was called iNAH, irregular near-field acoustical holography, and the other one was called deconvolution, which does the same then in the Farfield. And we learned that you can actually use both methods to quantify the source, allowing you to do, for example, source ranking analysis. And finally, we also saw a method where you can actually use a reference sensor to do a coherence analysis to actually reveal what is important to the users of your product. So here we are at the end of this web seminar. For more information, you can actually visit our website, and there you can also find some local contact details. And then I want to conclude by thanking you for your attention.